So now in this lecture, I'm going to talk about some limits of functions by L'Hopital's rule, and we'll see what is indeterminate form. We take an example so that x approaches 0, e to the 2x minus 1 over tangent 3x. Now first let us check what happens when x approaches 0. So we get e to the 0 minus 1 over tangent 0. So e to the 0 is 1, 1 minus 1 over tan 0 is 0. So you get 0 over 0. This is called indeterminate form. If you have this type of form, you can apply L'Hopital's rule. What is the L'Hopital rule? You just take help from derivatives. But this case derivative will be for individual terms. I'll take the derivative in the numerator and the derivative in the denominator independently. So take the derivative of numerator, you get 2e to the 2x, you know from chain rule. And the derivative of tangent x will be 3 secant squared 3x. Now let us put the limit. When I replace x by 0, in the top I get 2e to the 0 over 3 secant squared 0. So numerator is 2 and denominator is 3 because secant 0 is same as cosine 0 and they are equal to 1. So my limit is 2/3. Let us check this in the calculator quickly. So I'm writing e to the 2x minus 1 in the numerator, keep within parentheses, and divided by tangent 3x. Make sure that your calculator is in radian mode, otherwise you will see different answers. So I'm keeping this in radian mode. Now graph the function and take very small window. I'm taking -2 to 2, -2 to 2, because I'm interested to check the value close to 0. So this window is more than enough. So graph it and then trace at close to 0, so 0.00001 maybe. And you see that your answer is 0.66667. So it is 2/3. So our limit is correct. Example 2. Now I have 13 to the x minus 10 to the x over x. If you plug x equals 0, you can see 13 to the x is 1, 10 to the x is also 1. So 1 minus 1 is 0, denominator is 0. So the same form we are getting 0 over 0. So in this case, L'Hopital's rule or L'Hopital rule you can apply. So then what we should do, keep your limit, x approaches 0. 13 to the x, the derivative of 13 to the x is just like a to the x. You know the derivative of a to the x is a to the x natural log of a. So in this case, your derivative will be 13 to the x natural log of 13 minus, next one will be 10 to the x natural log of 10 over derivative of x is 1. Now again, if you plug x equals 0 here, 13 to the 0 is 1, so you get natural log of 13 minus that on 1, 10 to the 0 is 1, natural log of 10. You can leave your answer like this, or if you are interested to apply logarithmic properties, then you can say 13 over 10, or simply you can say natural log of 1.3. We are done with the second one. We'll take more examples. I'm taking example number 3, 2 cases. X approaches infinity, 2x to the 3 over e to the 5x. And another one is e to the 5x in the numerator, 2x to the 3 in the denominator. In this case, you can just understand simple way. E to the 5x is exponential function, so it increases exponentially. But the other one is cubic function. So in this case, you see e to the 5x is increasing faster. So in this case, this limit should go to 0. The other one, this is in the numerator, that one increases faster, so it should go to infinity. So we'll see how it works. First of all, when you say x approaches infinity, both goes to infinity. So the form in this case will be infinity over infinity, which is also indeterminate form. So let's apply L'Hopital rule. limit x approaches infinity, and remember we are expecting this result to be 0. So derivative of this one will be 5 e to the 5x. Derivative this one will give me 6x squared. Still it is going infinity over infinity when you plug it. So then further you can take L'Hopital rule. Take derivative one more time. Now in this case you get 12x. This one you are getting 25 e to the 5x. Still it is infinity over infinity. So we take the derivative one more time. So you get 12. Here you get 125 e to the 5x. Now you can see that the numerator reaches to a constant, but denominator still increases. So this whole thing, you can say denominator increases without bound. That limit goes to 0. The same thing will happen here, but other way. So when you apply all this process, you will see that this one will look like x approaches infinity. We'll get 125 e to the x to the 5x, over 12. Then you can see that the numerator increases without bound. So we understand that the whole function is approaching to infinity. So in this case my limit is infinity. I'm taking two more examples. First we need to see what happens when I replace x by infinity. So you can see that 1 over x goes to 0. So my numerator is 7 minus 0. And then tan inverse infinity, actually you know from the graph that tan pi by 2 approaches infinity. So then whenever you are going tan inverse, so then that one simply will be pi over 2. So in this case I do not have indeterminate form. So I don't have to apply L'Hopital's rule. I'm actually done. So when you look at this further simplification, you get 14 over 5. So you are done in this case. So you can apply L'Hopital rule if it follows the indeterminate form. Let us look at the next one. When I say x approaches 0, 0 to the tan is 0, sine 0 is 0, and x is also 0. So this one is 0 over 0 form. We can apply L'Hopital rule. Lx approaches 0. So derivative in the numerator will give me 10x to the 9. And then derivative of sine x will give me now cosine x minus derivative of x will give me 1. Now if I replace x to 0, my numerator is 0, cosine 0 is 1, so it's still 0 over 0. You can further apply L'Hopital rule. Limit x approaches 0. So that one will give you 90x to the 8. Derivative in the denominator will give you negative cosine x will give you negative sine x. You can further take derivative because still you are getting 0 over 0, but I want to apply a simple trick so that I don't have to take derivative anymore. So this one I will write like this: limit x goes to 0. I can take 1x from here, so it will give me x over sine x, and remaining is 90x to the 7. So we know that when x approaches 0, this quantity goes to 1. So negative 1 times, and this one is going to 0. So my limit is 0. All right, so we are done with this.